Well, hi everyone, and thanks for watching this paper presentation that I will be doing. My name is Richard Giles, and I'm a computer science student here at Georgia Tech, and I also work full-time at Micron, working on solid-state hard drives. So this paper that I will be presenting is called Exploiting Structured Human Interactions to Enhance Estimation Accuracy in Cyber-Physical Systems, and it involves a little bit of medical work and medical systems, which is why I chose the paper and am interested in it. All right, let's get into the paper itself and the presentation. But before going into the details of the paper, I would like to give explicit credit to the paper and its authors. I will also have a reference to the paper and its authors at the end of the PowerPoint, as well as here. The references at the end of the PowerPoint will encompass any other references that throughout the entire PowerPoint. So this paper was presented at the International Conference on Cyber-Physical Systems, and that was with the Association for Computing Machinery, ACM Society, and the Institute for Electrical and Electronic Engineers, or IEEE. And this was presented in 2015 in Seattle, Washington. So here's the ACM copyright number if you're interested in it, as well as the website URL to the document, so you can check that out. The authors of this paper came from two different universities, the University of Illinois and the State University of New York. Most of them did come from Illinois and one from New York. So of the authors themselves, from Illinois, it was Younglong Gao, Xiaohan Hu, Renato Makusi, Hongwei Wang, Minj Kim, Ho Liang Wu, and from the State University of New York, Lu Su. So a brief overview of this paper we'll be talking about is first and foremost hidden Markov models. So this is a key concept that is applied to their test case of a CPR responder system. I will go into detail of how the hidden Markov model works in the following two slides. The authors utilized the hidden Markov model in a combination with the CPR workflow, which is structured. As you can see in this example here, there are CPR steps that are very straightforward. One step leads to the next, which leads to the next, and there's a possible repeating of the steps. Some steps, maybe not for CPR, but in other Markov models will loop back to themselves with certain probabilities. So the idea here is that it's structured and has solid definitions of when to go from one block to another. In this case, a Markov model, these blocks would be called states. So this paper also goes over specific ground truth data, which is when you have data within a certain state, such as when a person is having CPR performed on them, and is compared to the baseline or what it would normally be in that state. So for heart rate as a measurement, it ensures that it is realistic according to the state that you're in. Sometimes a flatline 0 BPM might be realistic for a certain state, and there's also times where a flatline would be absolutely not the case. So it's good to have ground truth. So the cyber-physical data is quite noisy. It's not always going to be accurate. Interpretation of voice is not going to be accurate, and sometimes a sensor will maybe not have been connected to the in a CPR model, maybe only two sensors have been connected to the person in question, and a third sensor has been left out, and your system has to be able to account for that and basically interpret and know that that data is wrong. So this paper reviews how the data does not have to be 100% accurate in order to predict the correct current state by utilizing the Markov model. So the model allows for the use of received data from the sensors and to estimate the state transition and the likely measured data from a noisy sensor using ground truth. Okay, so here I'm going to explain hidden Markov models, what they are and how they work. So a Markov model is a model which is known also known as a series or a Markov chain. And that's because it looks at a sequence of events, such as the weather on day 1, the weather on day 2, the weather on day 3, and you can create an entire series of that and the probabilities and multiply them together, and that's sort of the basis of it. So it's able to do this by using Bayes' theorem, which is a statistical probability theorem in which you look at the previous sensory data or any other data in the previous state, and you are able to determine the probability of the next state and what will happen next. So here are some example applications of the Markov model or the hidden Markov model. So you can perform basic weather prediction. That is simply, you know, whether it's raining or snowing one day, or maybe what the temperature will be. But it's usually not that simple. However, you can also use it for power grid fault correction. So if you're have a substation or a transformer somewhere, and the measurement, say the current measurement on there is off, indicating that there's a fault, well, it could either be the sensors going bad, or the sensors being tampered with by a third party, or maybe the sensors legitimately picking up the high current data, or the data displaying and giving insight into the fact that the station isn't working correctly. Finally, you can use it for a CPR flow analysis. That's what this paper looked at. So a lot of the discussion will be about the CPR flow analysis, and I'll make relations to it. So here in figure 1, we have what is an example Markov model workflow. So each of the numbers is a state, so state 1, state 2, state 3, and state 4, and state 5. What we have is the objects that you observe in that state. So these objects, comparing it back to the CPR model, could be something like the heart rate of the patient, or the audio transcriber that is being used and what words are being said. So object 2 could be the word airway. And so then we have the probabilities of transitioning from state 1 to state 2, which is 1/3, and state 1 to state 3, which is 2/3. And so the system is able to utilize both the state transition probability and the object or the observed object data to best determine which state it will transition into. And here you have a system model, what would typically be used as a figure for this in a scientific paper of the Markov model. So Z is going to be your state itself. X is going to be the object space of that state, and Y is going to be the actual objects contained within that space. So Y is typically going to be equal to or less than the size of X. And this will go through for each of your states. You're going to have this data set. And sometimes the Markov model might loop back to the beginning. It might loop back to itself, loop back to new states, or come to an end. Really, the model can work however you design it to be. Oh, one thing I think I forgot to mention is that the Markov model, or the hidden Markov model, is based on the Markov model, but it's just that you can't observe the states. So instead of being able to observe directly, and in a CPR model say that, well, the person is in, say, state cardiac arrest, well, you can't observe that. Only the system can only observe what you have a sensor to. In this case, the sensor is only the heart rate and the audio transcriber. So it's able to make predictions on the state without visibly seeing the state. So onto the probability and the math behind what the Markov model is and how the Markov model works. I want to get into what the researchers covered, which is really just, so the first two probabilities are essentially what make up a matrix of preset or predetermined probabilities that you observed in the past. So in the case of CPR, you might look at the probability of going from one state to another and base that on previous historical data. And so what that is, for example, the transition between states, or the probability of transition between states. So what is the probability of me going to state P, or, oh, sorry, the probability of Z of T plus 1, given that I am currently in state ZT. So what's the probability of going to the next state, given that I'm in this current state, Z of T? And really, so that's predefined, and you would put that into the matrix in the system. And then you've also got the emission of an object in a certain space. So that's the probability that an object would be observed when you're in a current state. So again, if you're in the, I don't know, cardiac state in a CPR model, so that would be the state Z, and the object X, and what the probability of that is of happening. So what's the probability of your heart rate being within a certain range could be put there. So those are the two probability sets that we should really be given. And then there's the posterior probability, which we can use from Bayes' theorem. So what this is you combine the two formulas that we have previously, or, well, really the matrices. And what you're doing is you take your sensor data Y and you run it through Bayes' theorem to get the posterior probability. And this is the probability of how likely an event is to happen after all the background data and previous states have been accounted for. The formula gives you the probability of being in a state with a certain observable object given sensor data, so such as words or that the physician would say, or the heart rate. And this gives you the probability of state Z and the object associated with that given the sensor data Y. So plugging this into Bayes' theorem, we get the following. And so when you plug this into Bayes' theorem, what you do, what you get is you multiply the probability of certain sensor data given the emission of a certain object, multiplied by the probability of getting a certain object within a certain state, multiplied by the probability of being in that state, and then all of this is over the probability of the data. So once it's been plugged into Bayes' formula, or Bayes' theorem, what we get is the final formula, which is one which gives the probability of a certain sequence of events, that is the entire sequence, given all of the previous data, such as the previous objects, the previous states, and since this is a Markov chain, we have to multiply all those probabilities together. So you see right here, we've got the multiplication of all the probabilities, and really you're taking the maximum of all those probabilities, because this is going to produce an array of data. So your entire series goes from when I is equal to 1 up until t. So I is looping through for each of your states in this case. So if you're trying to calculate the probability for a 7 loop chain, then I would go from 1 to 7, and then you'd plug in all the values here, multiplying them out throughout, and then getting your final answer. So how is this done exactly? Well, you take the probability of given or seeing a certain object within the state, multiplied by the probability of observing a state given your previous state, and multiply that by the probability of your data given the emission of a certain object, multiplied by the probability of starting in the state in which you did. So P0, probability of Z0. So from the previous slide, we can utilize the math from it. And how the researchers did this is they developed an algorithm over here, which is going to allow us to maximize the posterior probability and optimize the state transition sequence. So let's go over exactly how this code achieves that. As the inputs, we have the OBS, or the observed objects. We have the state space, S. We have the object space, O. The start probability for given a time 0 start of an initial state. So basically Z0. And following that, we have three matrices. We have the matrix for the state transition probability, which is denoted by T. We have E, the probability for emission for that state, and the confusion matrix C. So all of these are input into an array format so that each state and each object pair have a respective data set. And once the algorithm is done, it will return Z and X. So for the actual code, we've got the first for loop followed by a main body segment that consists of 4 for loops. The first for loop is on its own. What that does is it loops through and initializes certain data. In this case, your V matrix, your B matrix, and your X matrix. So the V matrix is the maximum cumulative probability of that state. The matrix B is for storing what the previous state was, and X is for the objects being emitted at the current state. So after this initialization comes the main body, which is the for loops. I'll break it down into the first 2 for loops and then the second 2 for loops here. For the first 2 for loops, what it does is it loops through all of your observable objects as well as all of your states. And it loops through all of those and initializes what is going to be your probability max used for finding the max probability, the state in which your probability max occurred, and which object was being emitted at that time. So once all those are initialized, there are 2 inner for loops. These iterate through your object space and your state space. And what they're going to do is, again, in order to cover all the data points within the matrices, they have to loop through all of those iterations. And what it will do now is loop through the entire process and find your maximum probability. In this case, I'll go over what the formula itself is. So for the formula itself, it utilizes V, which is your maximum cumulative probability matrix. It takes the data point within there and it multiplies that by what is your transition matrix for that specific point, and then multiplied by your emission probability and your confusion probability. So after calculating what is the probability, I think we've all seen this code before where you simply say, is your current calculated value greater than your maximum value? If it is, you store it to the max value. If not, you continue looping through the for loop and covering each and every data point within the matrix. So after your maximum probability has been found, what the code does is it then stores the respective matrix location in V, as well as for the previous state B and the object that's being emitted X. After it's looped through all the possible scenarios and stored the max value, the code then finds the highest probability and its location within the matrix, which is these lines of code here. So basically says where did the maximum occur in what location, and then from there stores the state, and then is able to return Z and X. For observing the big O notation complexity of this algorithm, you can look at it in 2 ways, and that is by looking at either the space complexity or the time complexity. Most of the time you're going to be analyzing what is the time complexity, since you'll be working with real models that have filled out matrices. For space complexity, you'd only be concerned with the objects that are observed and the state space. In other words, your 2 inner for loops only have 1 iteration. From there, you can see directly that within the 4 for loops, if your middle 2 are set to 1 iteration, and your first 2 for loops on lines 4 and 5 are set to loop through all possible scenarios, then it's simply your the number of observed objects multiplied by the state space, which is your second for loop. If you're looking at time complexity, though, that is looking through the entire object space and state space, utilizing the inner two for loops on lines 7 and 8, it's easy to see that your objects, the observable objects that you have multiplied by the state space, again multiplied by the state space in your one of your inner two for loops, and then by the object space. And that's how we get the formula here where your state space is squared. Well, that's because we had two of those. And then the number of observed objects multiplied by the size of the object space. So the researchers looked at two different workflow models. They looked at a graph-based workflow and a tree-based workflow. I'll go over the graph-based workflow first and compare and contrast the results from that to the tree workflow in the next slide. Starting out with the first figure, we have what is the sensor accuracy, in this case noted as recall, but is really a sensor accuracy. So a case of 1, a value of 1 would be your sensor data is 100% accurate. That is, your heart rate data is 100% accurate. Your transcriber information is 100% accurate. And fidelity here is the overall workflow accuracy. So did your hidden Markov model predict the correct state? So you can see that obviously as you increase your sensor accuracy, you're going to increase your system accuracy. But what's interesting is there's only an upside for using a workflow, a hidden Markov model in this case for the workflow, because you're always going to have higher system accuracy using that compared to just raw data system usage. So the next graph, figure 4, is the node degree. So when you're using the graph-based workflow, you can specify the number of nodes. This graph simply shows that as you increase the number of nodes, your system accuracy decreases. So it's best to keep the degree on the lower level and to keep using the Markov model. Figure 5 shows the path length and compares that to the system accuracy and finds that you do want a higher level of a path length for your system. But also, again, the Markov model for both the workflow aware estimate of objects and estimate of states are following the same trend where they are both more accurate. But you are finding that the workflow aware estimate of states through the previous 3 graphs has always been higher, and on the next graph becomes significantly higher. So the final graph is showing us the inter or intrastate object similarity and how that compares to your system accuracy for both the estimate of objects, estimate of states, and raw measurement systems. And the clear, more accurate system here is going to be your estimate of states system, which has nearly a 100% accuracy of the system given a variation in your object similarity. So if your words are too similar for your transcriber for between your states, say, then you wouldn't want to use the estimate of objects workflow. You'd want to use a states workflow, which overall makes more sense. So next we have the graphs for the tree-based workflow. Starting off in figure 7, we have the system accuracy plotted again versus the sensor data accuracy measurement. So if your sensor is 100% accurate, again, you're expecting 100% system level accuracy. But again, just like with the previous graph model in both and also in the tree model, you're seeing that the hidden Markov model systems are being more accurate than the raw sensor data systems. So again, that's sort of a win there for that. Okay, next we have path length, which for the tree-based workflow model gives a similar result to the graph-based workflow model in that as you increase your path length, you are finding that the workflow aware estimate of objects and of states, again, is more accurate than your raw data. So for the next figure, which is figure 9, We have the comparison of the number of objects contained within a node or within a state, and compares that to the overall system accuracy. So what you're seeing here is there is a variation between the number of objects in a state, but it could be attributed to noise. Main takeaway from this plot, though, again, is we're seeing that the modeled system, the hidden Markov modeled systems, are performing at a higher level of accuracy. And then a similar, so back onto figure 10, similar to the graph-based workflows and the tree-based workflows, again, we're finding that the estimate of objects workflow is not as accurate as the estimate of states workflow when you have objects that are similar. And then if you look at the system accuracy, it's nearly 1, if not exactly 1 for the estimate of states system, which is overall going to be the better system here. So the researchers came up with this system, which is the hidden Markov model for the CPR workflow. And what it has is a start and really an end, or a place where you keep looping to, and goes through, and it has the probabilities for each state, but also the objects here. So over here on the right side is going to be your objects, or really the word that is interpreted from the transcriber on the system, and will work and use that information with this system to calculate the next state, or the most likely next state. Okay, so for the conclusion for this presentation regarding the Markov models and the CPR flow is that the sensor data accuracy, or how it's used, can be increased if you're using a hidden Markov model or a Markov model. However, it has to be used during a structured process. So you can't just throw a hidden Markov model at anything. It has to be structured. So moving on from that, so the estimates of states workflow has the higher accuracy compared to the estimates of objects workflow when we were comparing the two between the tree workflow and the graph workflow. Between the tree and the graph workflows, I will say that the tree workflow is slightly more accurate. However, the two are comparable in their differences, and that the bigger difference comes between the estimates of states and estimates of objects comparison, as opposed to the comparison between the tree workflow and the graph workflow. And finally, the medical and computer collaboration that went on here can be used to potentially reduce the number of mistakes during high stress situations, such as when CPR is being performed in a first responder situation. Before I finally end the presentation, I just want to give a brief slide for the references. I'm not going to go through each reference, but just know that it is in the slide deck. If you're interested in any of these references, you can open the slide deck from the link provided in Piazza and click on any of these links to access the material. All right, and I finally want to open it up to questions. So I know that since this is a video recording, they'll all be on Piazza, so please ask me a question on there.